My name is Aditya Mohite. It's like mojito with an E. So you always butcher my last name. And I am in the Department of Chemical Engineering, but I really have a physics training. So I'm kind of masquerading as being a chemical engineer, although my colleague is here, so hopefully she won't tell on me, right? But she, she does a lot of optoelectronics too and physics too. So, I'm going to tell you about single photon emission today and a platform that we've developed, which we feel is it's a really exciting platform because it tends to deliver everything that you need for a single photon emission: brightness, purity, stability, right? Short lifetimes, and that's come out of just looking at the structure property relationships in a new material called halide perovskites. I hope you may have heard of this. So I'm going to talk about that. The other role I also have is I am also the faculty director, the first faculty director of reInvents, which is the School of Engineering's energy transition initiative, right? Looking at sustainability problems. And I'll just talk a little bit about this, maybe one more slide about the different projects that are ongoing, at least in my lab, in this area. But really this project is funded by, it's a NSF STC center, a science and technology center. It's again a big program. It's one of the, NSF has these big programs you may have heard, like MERSECs and STCs and ERCs. So STC is one of those centers. And this is led by University of Washington by a really amazing guy called David Ginger. He's the PI of this and also a good friend. And that center is called IMOD, Integration of Modern Optoelectronic Materials on Demand. And the premise of the center is to be able to take materials that are in principle solution process and build the next generation of classical and quantum optoelectronic devices. Okay? So that's kind of the theme. So before I talk about it, I just want to give you a flavor of the kind of things that we do in our lab. It's really, we look at, we have a really nice program on looking at solution process materials, and of late we've been looking a lot, last 5-7 years, with this new class of materials called halide perovskites. And so we do a lot of structure property relationships, but also a lot of cool physics experiments. It's a very interesting material. It's a soft semiconductor, which means that if you think of silicon or gallium arsenide, the way you define the softness is that it's the Young's modulus. It's 1/10 of that of silicon, right? Which means it's a flexible material, not quite as flexible as organics, but it has an organic component. And so what happens is when you have external stimuli on this material, temperature and light and biases, it does things to its structure. It fluctuates and it moves around, and the lattice kind of distorts, and that gives rise to really interesting photophysical properties. At least in the context, you guys are all mostly physicists, I would imagine, or physical chemists, or in that flavor, right? But it gives rise to a lot of very interesting properties, okay? So we have a really nice program, and we've done a lot of work on this, and I'll talk a little bit about this. Another thing that's evolved from it, I also have a big program on solar, conversion of sunlight into fuels. And we just launched a company called Direct H2, which produces green hydrogen. With a lot of techno-economic analysis, we've come to this point of a cost range of $2 a kilogram. And that essentially integrates these high efficiency solar cells into almost what are commercial electrolyzers, not quite, just a little bit of tweaking. Okay? And what this does is it takes away the cost of electricity, which is a huge deal, right? When you're building something and you think of electrolyzers, you have this 30-35% cost, which is electricity. And so it takes that away, and so that's that company, and that's doing really well. So that's the third thing. The second thing. The third thing that we work on a lot is called the Plasma Foundry. We've just launched a very big program about a year and a half back on looking at cold plasmas or non-thermal plasmas and convert feedstocks like carbon dioxide and methane into value added products. And here we are really leveraging, at least I was at Los Alamos, where we build a plasma reactor for doing different things, right? But the idea was to leverage the Boltzmann distribution of the electron temperature, right? The hot electrons. When you dissociate, you create a plasma, you get these electrons which have very high temperatures, tens of thousands of degrees. And then the idea was to use that and do chemistry with it. Okay? So that's kind of what we've done. And it's a big program and a lot of exciting things are happening. And then the fourth area which I will talk about today is this idea of deterministic growth of quantum emitters, right? And there's a lot of words, but what it does is we want to be able to place, as you may have heard from other talks, a quantum emitter precisely exactly where you want it to be, and you want it to have all the properties which are good for it, right? So please stop me if there's any questions, but this is kind of the flavor of things. So let me talk a little bit about what these halide perovskites are before I go into details, and you'll see more things. I have to admit I put this together just this morning, maybe literally in the last hour, so it's a little bit scattered, but I hope I won't let you down. Okay? So halide perovskites are like salt, common salt. They are ionic semiconductors, and they have this ABX3 structure, right, or AMX3 structure, where you have A, which is a cation, a monovalent cation, things like formamidinium, methylammonium, cesium. M is your metal, or B is your metal. It's a divalent metal, lead, tin, germanium, any divalent 2+ metal that you have. And then the X site is an anion, right, with a minus charge, and that's the electrostatics of it. That's what you put all of these things together. And typically this X in the halide perovskite is a halide. It's iodine, bromine, chlorine, right? And if you just walk across to Ramy, right, Lane Martin makes the same type of things, but he makes a lot of perovskite structures, but these are hard materials. These are like ceramics, right? Lead titanate, strontium titanate, calcium titanate, and multiferroics and things like this. So this is a mineral that has been around for a very long time, but this is the halide version of this, right? And hence these are called halide perovskites. There are three main types of this. There's a formamidinium. All right, so back up. So I take all these things, right, and I put them all together in a solution, and I make a film of these materials, right? How do I know if I've made a perovskite? Well, obviously, it depends on something which is known as the tolerance factor. Tolerance factor just comes from the fact that you have electrostatics, right, which govern everything because these are charged entities. And so everything in terms of the size and the charge has to fit together. And so if I take the ratio of all these ionic radii, there's a formula for that. It turns out that this tolerance factor, if it falls between a range of 0.8 and 1, then I get a perovskite phase. And if it doesn't, then I don't get a perovskite phase. So if I take the three simplest ones, this first one is formamidinium, lead triiodide, right? I put the Fa cation. It has a tolerance factor of almost 1, so it's right on the edge of what you can make, right? In fact, it's not, right? It's a little bit bigger, okay? So it's a bit fat. If you look at the bottom one, that's cesium lead iodide, cesium small, right? And so it forms a perovskite that is 0.8. That's on the other extreme, right? So it's really small, right? And methylammonium is perfect. It's right in the middle, right? It's 0.9. And so that forms a perovskite, but it turns out that if you look at these three things, the top and the bottom don't really exist as perovskites at room temperature, right? They are in what is known as these delta phases or yellow phases, and so that's a problem, right? So either I need to do something to compress the top one, right? Make the lattice slightly smaller, or increase the bottom one, right? Increase the lattice parameters, somehow have so that it actually goes up. Methylammonium is great and it forms a perovskite, except the problem is it's even more sensitive to moisture than common salt, right? So you've been in Houston now for a while, and if you put your salt, right, trying to put salt and you'll see no salt comes out because it's all agglomerated, it's hygroscopic. This is worse than that. And that's obviously a problem. You don't want this material on your roof for making solar cells or any optoelectronic devices. Okay? So that's the thing, and so people do a lot of things around it. Now, in addition to this, there is also a family which are these these layered materials, which are known as these two-dimensional perovskites, right? What you do is, I have the same thing. It's the same perovskite octahedra, but I put an organic molecule that's much larger, so it can't really go into the lattice. And so what it does is assembles and it forms a layered structure. Okay? And so those are these layered perovskites. They are known and they have these formulas, which are written here. I won't go into details of this, but things like Ruddleson-Popper, which is also a phase in the oxide perovskites, and Dione-Jacobson, an alternating cation, and that just says how all the structure is kind of arranged, right? Slight offsets in the lattice constants and lattice parameters, and that's the idea. But the nice thing is that you can do a lot of nice things with it. You can tune the chemistry, so I can change the number of layers, right? So it's like, I can have, you can see N1, which is just single layer of the perovskite with a spacer cation. I can keep going and control that chemistry very well in the lab. So I can get 2 layers and 3 layers and 4 layers. And obviously, as physics students, this is perfectly like a particle in a box, right? You're changing the quantum confinement, and so you start to see those changes. In fact, this is what you see. On the left, you have absorbance. As you go from N1, you see a sharp resonance. This is the dominant resonances in these materials are excitons, right? And as you move to N6, you can see that this excitonic resonance starts to get weaker and weaker. Your binding energy of the exciton gets weaker and weaker. You are decreasing your quantum confinement, right? And corresponding photoluminescence, you can tune this very beautifully, okay? So I won't talk so much about this, but I wanted to give you a flavor of these materials. And one of the things our lab has been really famous for is, as I mentioned, the bane of these materials is stability, long-term stability. And so we hold the record now for the 3rd year, we just had this, for the most stable perovskite in the world, right? And so we're working with a lot of companies in trying to license these things out. And in fact, the litmus test for this is this paper that we published. It was, this is an accelerated aging test that you would do on a solar cell that is made of this, right? And you would set your, you would take this solar cell, put it at 85 degrees C and put light on it and forget about it, right? Write a program so it keeps measuring your power conversion efficiency, and what you want to get is a straight line like that, like a really flat line. You don't want it to drop, and that's really accelerated. And then you kind of come up with an Arrhenius type model and figure out how long the solar cell lives. Well, it turns out if you do all of that, this solar cell would live on your roof for about 18 years, right? This is not us. This has been externally validated by a major or 2 major PV giants, right? So we are very close. And this was really appreciated by the audience, and I mean by the people who read it. This also appeared on the cover of Science, and I've never really tried for covers. This was my first cover, and I'm not trying to gloat about it, but my wife designed this cover. So she said, if you don't show this, don't come home, right? So anyway, so yeah, you had a question. Yeah, so these are all encapsulated, right? And so there are different types of tests you run. You could do a test which is 85 degrees, 85% humidity, relative humidity, and 85 degrees C. That's a dark test. But you could also do things like this, which are light in temperature, then you don't have any moisture. It's an encapsulation that people use. So there are different types of tests that you would run, right? So that one was done with encapsulation in ambient, but with obviously encapsulation which does not let moisture in or air in. Okay, good. So that's all about perovskites. I won't talk more about this. But that's really the background of where we kind of started this work. And so I want to talk about single photon emitters. I'm guessing most of you have had an overdose of this because a lot of people work on this. Yes? No? Kind of? Yeah? Single photon emitters. Everyone gets this more or less? No? No, okay. It's just you know, so single photon sources are great because it's essentially like water dripping down from your tap, right? And you want the water to come down in drops, right? One drop at a time, right? Not when you open your faucet, all of these photons or these droplets coming down together, each drop coming down. Not only do you want each drop at a time, but you want that each drop of that water that comes down is precisely the same shape, volume, everything about that drop is identical. Those are, you know, indistinguishable, which means if I look at one drop and the other drop, I cannot distinguish, right, apart from the timestamp, right, when it arrived. Okay? And obviously I want that rate to be pretty high, right? I want that continuous flow of the drop coming down. If I have a drop that's slightly smaller and the other one slightly bigger, that doesn't work for me. Okay? So that's what you desire, and single photon sources are photons, so you need them to be emitted like this so that each photon is completely identical. Okay? And if I can do that, then I can do quantum computing with it, I can play games with it, I can get these photons to interact, right? You know all of that, right? Quantum algorithms and all that. People do this with AMO, right? Atomic and molecular, I'm sure you'll hear a talk about this. They use these BBO or these non-linear crystals, they create these two photons. Essentially, these are like twins, right? Coming from the same crystal. And then because they are the same DNA, you can kind of play around with it, right? So that's really the way to do it. But what we are trying to do is create that with a material, something that is emitted through a material, okay? It's really a platform. So I guess what you want is you want single photon purity. They do this G2 measurement. That's the correlation between detectors, right? And you want this single photon coming in. You've heard of this Hanbury-Brown twist experiments, right? You have essentially a source that's emitting. You have a beam splitter and two detectors, right? And so if you have single photons, either one of the detector will sense a photon. But if it's not a single photon source, obviously there'll be an event where both of them go blip, right? And you don't want that. And so that measure, this G2 measurement really measures that, right? And you want this whole idea of indistinguishability, coherent, which means they have to be indistinguishable, like I said about the drops, right? Water drops. It has to be very bright, which means I want that rate to be, you know, something of the order of 10 to the 4 photons a second, right? That's the kind of level. And that typically corresponds to a unity quantum yield, 100% photoluminescence quantum yield from that object. I want to have the option of electrically biasing this, not just with a laser, because imagine I have an optoelectronic circuit and I don't want a laser coming in, right? And I have to worry about this, right? If I put it in a cavity, if I have a way of electrically biasing this, we know how to do this well. Microelectronics is a platform, so you want that. So I say chip scale integration, and I want room temperature operation. That's really hard to do. State of the art is with gallium arsenide. They all do this at low temperature. This is all low temperature stuff, right? When you hear single photon emitters, and you know, it's typically always low temperature stuff, right? Okay, so that's kind of what we want to do, and I just want to say that the state of the art is this, where they take gallium arsenide, right, and they embed this in aluminum gallium arsenide. These are buried systems, okay? And so we wanted to do this with perovskites, right, and really see what we could make, use that platform, and inspired by that idea that can I really create a quantum dot within that perovskite matrix, okay? Some slides may be repetitive. Okay, I keep moving on. Yeah, so the goal was to develop a platform where quantum dots exhibit brightness, purity, and allow for electrical injection. And we wanted to do this using a synthesis process that, you know, with our expertise on thin film synthesis, we wanted to do that. One of the big challenges in this field, right, you'll hear people giving, you'll hear people giving talk about nanocrystals, right, all kinds of nanocrystals. Whenever you have a nano object, you have huge surface to volume, right, we know that. And so whenever you have any of these objects which are emitting light, you have a lot of surface, a lot of dangling bonds. And so what people do is they want to be able to passivate this surface, right? Somehow prevent those surface states, or you don't want chemistry to happen, right, while you're doing this measurement. You want this to be super stable, right? And so that was the idea, and that's one of the big issues in this field. In perovskites, it's even more sensitive, at least in the colloidal, like in the 2,6 systems, cadmium sulfide, cadmium selenide, cadmium, they put a cadmium sulfide shell, right? Munji Bawendi got the Nobel Prize for, trying to get these, and they make LEDs out of it, right? In perovskites, it's even harder because I told you it's a soft material. So imagine it's like cotton wool, like cotton ball, right? You've seen those cotton balls. Try to do some chemistry on that. It's very hard, right? Even if you manage to put some ligands or some kind of shell on it, it doesn't remain stable, right? Because it's very, very soft. So that's an issue. So we wanted to overcome that. We want to suppress this idea of blinking and bleaching, which is a huge issue. This is just changes, your emission is not very stable. And get to intrinsic line widths, right? Essentially determined by the Heisenberg's uncertainty principle, right? H bar by 2, you want to get to that type of limits. And so the intrinsic line width for these systems would be something of the order of, I think, I want to say 0.3 milli electron volts, 300 milli electron volts, or 100 milli electron volts, or 0.1, so micro EV, something of the order of 100 micro electron volts, right, at low temperature, extremely, extremely sharp. That's almost like a molecular system, right? Molecules have very sharp lines because they have two-level system, that's all they have, okay? Okay, and I want this to be able to print, right? I mean, if I can print these materials, in a facile way, so I want all of these things. That's asking a lot for a material system to do, okay? All right, so we've developed this process which is where we can make these bedded quantum dots inside a host of a 3D perovskite, okay? It's really simple. The way we do this is we take one of these halide perovskites. This is formamidinium lead bromide, okay? And we add a type of additive in there, right, which is an iodine source, okay? And for example, we'll add a 2D perovskite which is iodide in it, and then we do a certain annealing step, right? And what we end up getting is we grow quantum dots, but now they are embedded inside this 3D matrix, right? And so that's what that looks like, that cartoon. But when I look at the photoluminescence, this is what they look like. So I see the green. That's the background, that's the host matrix. It's a large band gap. So you see this green color, but then I see these dots. These red dots are these single photon emitters, right, at room temperature. This is what I've grown. If I put a filter, a green filter, right, on it, then I get essentially these dots which are emitting, okay? And at room temperature, what you see is this, where, you see this is photoluminescence as a function of excitation energy. And you see the host matrix, right, that's 2.2 electron volts. But then you see this emission which comes from, with just about 2% of doping or additive, you start to see this emission around 1.6-ish, right? That's coming from these iodide quantum dots that have now grown, okay? End workout, okay, good. So, all right, and so this is a very facile method. We have done it now with a lot of things, right? We've grown the formamidinium lead iodide quantum dots also in even a wider band gap, like 3 eV band gap or almost 3 eV. That's chlorine, and so that's what you see. You see these sharp lines at low temperature. These are all single photon emitters, right? And the line widths are really sharp. Look, I mean, you can get to as much as 0.89 milli electron volts, 890 micro eV. So you're right in the range of where you're getting to the intrinsic line width of these materials, okay? And these are extremely bright, right? They're extremely bright, which means they emit at about 10 to the 3 or 10 to the 4 photons per second. So they are very bright and very stable. I'll talk about the stability as well, okay? So that's really the story, and you can look at them in TEM. It's very hard because FAPB BR3 and FAPB I3 are about the same lattice constants. So it's extremely hard to get contrast, but we worked with someone who's very talented, Sandhya Susarla. She's an assistant professor at Arizona State. She is an expert at looking at these TEMs. She looked at this, and verified what these dots were. They were indeed objects, and there's a lattice constant around it and all of that, right? So all of the good stuff, right? And we verified all of that. So they were indeed dots which were embedded in this matrix. And they had very similar lattice constants, which means they were perfectly protected. It's kind of like a core shell structure. I have a dot, and then I have this huge matrix, right, around it. So it's almost like someone sitting in the middle, and you protect it in the room. If there's a storm outside, it doesn't really impact the person here, right? Maybe it'll impact, maybe it'll break a window, but if you're in the middle, nothing really happens. That's kind of the idea, okay? Right? And so you see a lot of emitters. They have different energies. So this is what you'll see, right? You'll see these are 4 dots in a single sample, right? And that's what it looks like. And you can excite that dot locally. You can go below the band gap photo, excite the dot, look at the dynamics, and look at this. This is about 133 micro EV. That's the best we can do. I told you that the intrinsic line width of this is about 100. Maybe it's a little bit below 100. But we are right there. So this is the intrinsic limit of what you can get, right, with this. And this is really the state of the art today, okay? All right, did I miss something? No, okay, good. And these are extremely stable too because they are protected, right? They are not susceptible to doing chemistry on the surface. So you can see, so that's your G2, right? So the G2 is about 0.1. So if you have a G2 signal, as I said, it's below 0.5. That means you have single photons coming out of this. And look at the stability. They're extremely stable. You don't see any blinking, bleaching of these systems. We also measured this over 4,000 seconds. That's an enormously long time for these type of measurements. And they have this really short lifetimes. You have 246 picosecond lifetime, right? And this is the radiative lifetime of the exciton. Obviously, the excitons, they are short-lived, right? They want to recombine. They don't want to stay like this, right? They're not free carrier. They're not screened. So they want to do that. And there is something which is called this coherence lifetime. Do you guys know what the coherence lifetime is? Which is, we talked about this purity of the photon and things like this. So you want that to be equal to this lifetime, right? Which means that as long as my photons, my electron hole pairs, as long as my exciton's really living, or I can do computation there, so that's the best I can do. And so we get something which is order of T1 by T2. We get a coherence lifetime of about 200 picoseconds. That's really, really long, right, for this. So that's kind of where we are, right? And you can look at really super cool exciton fine structure physics, right? So let's look at, these are dipole selection rules, right? You can kind of predict some of this. But let me see. So for example, if I have angular momentum of 1, I hope you remember this. You have a triplet state, right? But if you have an angular momentum of 0, I hope you remember your quantum mechanics. That's a singlet state, right? The electron and hole have half spins up and down. So that's what you expect. And so in our measurements, right? So and what I can do is I can break that symmetry, right? I can apply fields, electric fields, magnetic fields. I can break that symmetry, right? And I can look at the cool physics. So when I look at this as a function of magnetic field, this is my single photon emitter, right? With the phonon sidebands and whatnot, okay? And this is actually a triplet state because the quantum dot is not perfectly spherical. So it has the structural symmetry is broken, right? And the structure within even the atomic scale, it's tetragonal, it's not cubic. And so you break that symmetry and you get the triplet state, which becomes the really dominant emission state. And then I can apply magnetic fields. You see this beautiful Zeeman splitting. But you also see that the singlet state, the dark exciton, that starts to become now allowed, right? The magnetic field breaks that symmetry, and you can start to see this come up. And these are all the things. So this is the triplet splitting. This is the, I guess this is the singlet bright splitting. All these type of analysis that you can kind of do, right? Extract the G factor and whatnot, right? And this is very simple. You can just take a finite, finite well model like particle in the box with finite potentials. Right, you know everything, and you can calculate that. This is just really, simple quantum mechanics, right? As you will, 101, and you can predict, the dark bright splitting, the size, and how that changes, and all of that. It's a little bit complicated with composition, but you can do all these beautiful things. Okay, and in addition to this, what you can also do is because now it's a film, it's a bulk film. I can drive this electrically, right? So I can just make an LED, Push this down at low temperature, apply a bias, and that's what you see, right? You see these single photon emitters, right? Now, but they are electrically excited, okay? And you see these interesting things about, we actually see, a trion. We also see maybe a biexciton and things like this. These are things that we are trying to kind of understand. But you can get this G2 measurement, you get 0.44. That's telling you that it's emitting single photons, right? And electrically getting single photons is very challenging, because imagine you have single photon emitters and I apply a voltage. If I have to apply, say, in this case, 5 or 8 volts, whatever it is, right? I apply that, which means I'm exciting simultaneously many dots, right? They're all emitting. So it's very difficult to get it precisely, so that's kind of one of the challenges. We did this with Doug Natelson's lab here in physics, but we can do this now on our own in our lab as well. But so that's kind of what we do. So that's kind of where the story is, and so we're excited about this platform. And the next thing that we are doing is now printing these dots, right? Can I do this chemistry where I can do 10,000 dots at one time, right? And so what we are working with is through this iMod with Professor David McKenzie's lab at UW. He has this really amazing electrohydrodynamic printing process. So where each drop of each, or I guess they take a solution, each drop size, the volume of that is femtoliters, right? Femtoliter drops, so they can, we put a precursor in, we have a wet film, they come in and they can put down these dots, and they can do it at very high throughput, right? They can print 10,000 of these dots. Okay, so we are going, instead of doing this, now we want to go to this top, you see the top right thing? That's kind of where we want to go, right? And I think it requires some work, but obviously, the non-physics side of me wants to do scale up, right? I want to do something that's practical and that's applicable. So you want to think of both these areas, while you, of course, the photophysics is all very nice, right? So that's kind of where we are. We've had some initial results. We are able to print these now. So you can see these are all now dots that we've printed. This is still, work in progress for us. And of course, the cool thing to do is put it in a Bragg mirror, right? Put it in a cavity. I mean, this whole NRT is about cavities, right? Even if you don't want it, you'll have to put it in a cavity. We all of us are in the damn cavity, right? So that's what you do. You put it in a cavity, and you can get these cool effects. We've got these Bragg mirrors from Vinod Menon, really amazing guy. But we want to be able to make electrically tuned sources of single photon, putting them in a cavity. So those are all kind of things that we are doing. These are results from the cavity, very initial results, right? And we are able to get pretty nice line widths. This is all work in progress as well. Okay. So well, that's all I want to talk about. So yeah, in summary, I mean, I just leave that out for you all to read, but I will be happy to interact and chat with you about things. We are looking to see if people are interested in this project of trying to build these single photon emitters, right, and work with them. Okay, thank you all.